We have Byron Davies, who I think is actually trying to make the world a better place.
Right.
And let's hear about that.
In a couple of different ways. First, I'm advertising my next year's talk. I have a startup now called blackswanlearning.com, and you can ask questions about that in the question session. But for this, I'm representing Autopilot, LLC. We've been working on something for the past few years to figure out how to apply a lot of the things that our famous ancestor Dijkstra did in software. And so I'm going to go through this, our goal, fault-free code. I'm going to talk about the thought leaders. I'm going to go into a little background about Dijkstra and others. Talk about our weakest precondition approach to producing fault-free software. I'll give you some examples and then a demo. Bugs have been around forever, of course. There's been some approaches to preventing bugs, and none of them perfect. But they differ in one sense from what we're doing because they generally refer to brand new code, for developing new code. And problem is there's a lot of legacy code out there, and it turns out in the life cycle of software, well over half of the money is spent in maintaining code rather than writing new code. So we asked, what if there's a method that could find bugs in legacy code? And what if a variation of this method would also help you understand that code? Because most of the people coming in and looking at legacy code are new to it. They have to figure out what it does because the documentation is imperfect. And so we'll talk about that. And we call this method systems integrity assurance. So these are some of the people in our past. Edgar Dijkstra, of course, he's just a god in computer science. Bob Floyd was, and invented the weakest precondition method and Dijkstra Guarded Commands, which we'll talk about. Bob Floyd was another early innovator in applying logic to software. Scholten helped Dijkstra with the mathematics. Oh, actually, I'll go on. I have that on my slide. I don't have to write it down here, or don't have to think through it here. Scholten helped to formalize the mathematics, and Chandy and Misra extended the approach to non-deterministic and parallel programs, which we'll also talk here, because a lot of legacy systems are not just straight-line programs, but involve a lot of things going on at the same time. We need to deal with those as well. So weakest precondition. How many people are familiar with weakest precondition? Oh, a handful. So it's basically a method, and you can think of it as figuring out, and you start, and let's just take a piece of sequential code, and you say there's something you want down here. You want to trace back up through the code and say, well, what is it that has to be true and the minimal thing that has to be true in order to make sure you get that result at the end of the code. So there's a lot, just like half a dozen simple rules to compute weakest precondition. And it's basically, we're going into the transforming programs into the logic space rather than the programming space. So weakest precondition operates on a small piece of software and a postcondition and produces a precondition or computes a precondition. So summary of weakest precondition. Somebody complete this phrase for me. The road to hell is paved with good intentions. Well, there's another thing. The road to hell is paved with bad assumptions. And in fact, I look back in my life, and I think every place where I made a disaster, a serious error, was because of a bad assumption. And so we say we need to check your assumptions, and we abbreviate that by CYA. And so the weakest precondition is a method of checking your assumptions. And then there's another version of weakest precondition, which is kind of analogous to what Amina was talking about with symbolic evaluation. Symbolic evaluation, you basically evaluate all the trees with symbolic variables and propagate those symbolic variables down the evaluation tree. Slicing works in the opposite direction. And so if you want to understand what a piece of code does, plant postconditions, but abstract postconditions at the exit of that code, and then figure out what transformations had happened to that code by going up and just following weakest precondition applied to those abstract values. And then there's a general version. So there's been a lot of people who thought about weakest precondition, but there's a more general version of weakest precondition. I'm talking about sequential code, basically, that weakest precondition can also be applied to non-deterministic code of systems and systems of systems that work non-deterministically. And so I should go back because I missed some people in this picture here. And these are the members of Autopilot. This is me, of course, and this is Jack Ring, who's a systems guy. I mean, he worked on missile systems back in the 50s, software for those. Oris Friesen, who actually implemented the first relational database system. This was not at IBM, it was actually at Honeywell way back when. And this is our chief technical officer, it's Tony Pizzarello. And he had a history, back in the 90s, he developed software basically to debug code. He developed first a method based on weakest precondition, and then some software to support it. And then he got sidetracked because this Y2K thing came along. And it turned out the formal methods that he developed were perfect for finding Y2K bugs. And so he went off and made a lot of money on that. And then, of course, once Y2K had happened, well, that business kind of tailed off, and he was out of that. Anyway, he's the kind of the genius behind all of this, and has figured out this. He and Oris have written a 200-page book detailing all of this work. And when we started on this, we had the idea, because we knew these are going to be big problems. We start getting to big pieces of software, that these would be big problems. Has anybody heard of the Micron Automata Processor, or AP? Hardly anybody. One person. Yeah, all right. Well, this is a device based on memory technology, but a device that deposits tens of thousands of finite state automata on one chip. And they're kind of recognition devices. And so on a single board, you can have about 1.5 million finite state automata all working in parallel on kind of recognition problems. And so when we went into this, we thought, well, gee, if we could just somehow get this working on the SIA problem, then we'd have something really fast that would work on oodles of code rather than just simple programs. We haven't figured out how to do that yet, but if anybody wants a challenge and is interested in finite state automata, this is an amazing system. It's really good for recognition. Can really recognize. You have a stream of data coming through, a gigabit stream of data. It can recognize very complicated patterns appearing in the data in real time. And so if somebody wants to write a Racket interface to that would be awesome. So we get into our tools. Here's kind of the steps that we have. Start with a program. There's some problem with the program, probably a bug. We go out and find the code for that program, and then we pull in all the related code for that program. Then we go through a process, and you can't read it here, but you'll see it on the PDFs, of generating the Dijkstra Guarded Commands to represent the program, and then doing weakest precondition. And so we go through all those steps. The expand step in other languages would be lex parse, semantics, and et cetera, et cetera. Fortunately, in Racket, those are consolidated pretty much, and this is, here we'll go. Here, actually, we'll paint the whole picture here. So we do the weakest precondition, but the weakest precondition requires a postcondition based on the problem we were having in the code when we're working on legacy code and we have a bug. We have to identify a postcondition that says, well, what should have happened at that point? We feed that into the weakest precondition to get to, and then we simplify, and this can result in a large logical expression. We simplify that, and then go on to later steps, and then find the fault. So we did this, created the Racket program, going out, finding the Racket code. So we start with just a call, basically, or something like that, or a complex of code. I'll go out and pull in all the functions that used. We then convert it to Racket syntax for the analysis, which puts it into a linear form. It's useful for the weakest precondition. We generate Dijkstra Guarded Commands. And when I went into this, I was really hoping, this would be really general. We could convert things to Dijkstra Guarded Commands. We have C code with Dijkstra Guarded Commands and other things with Dijkstra Guarded Commands. I have this common language. And then I realized, of course, that they have different abstract machines. And so you have to deal with that problem as well. And so yes, we have it working. I'll show you a demo. And one of the let's see. We'll talk about the history a little bit. 2 years I came to the Racket conference for the first time because I was thinking about Racket. And I saw Jay McCarthy's talk, and I thought, yeah, Racket will work for me. So we started doing this in Racket a couple of years ago, and it hasn't been a full-time deal. Let's see. Here we go. And after working on it for a while in Racket, I discovered the syntax browser. And it turns out that this was just a phenomenal tool for us. Syntax browser allows us to bring in code. So we have a basic, or have a list of examples here that we're going to run the method on. So we selected a piece of code. It calls the hysteresis function, which is this one up here. And so we expand that. While expanding that call, just turning that into syntax provides very little information. And so we have another step called unroll, which is really lambda substitution, and a couple other things that now turns the entire piece of software, including all of the functions brought in from files and so on, into syntax, the Racket's intermediate language. And I'll close that window because we have limited screen space. This looks a lot better on a 27-inch iMac screen. And then there's just a simple flattening step that gets rid of the nested begins and so on. From this, we can calculate the Dijkstra Guarded Commands, and this is a Lispified version of the Dijkstra Guarded Commands. But we can also do things, for example, for weakest precondition analysis, we can calculate a path through the program. Because all right, how about if we get rid of this one and go over here. So this is the syntaxed path. So this is basically going back up through the program to find the set of operations that you'll need in order to compute weakest precondition. And of course, Lisp doesn't make that easy because Lisp is threaded downwards, and so it's a little tree walk to get that path. From that path, then we can calculate, for example, the variables in play at the point of evaluation there, or we can compute a slice of this code. And what the slice is just using an abstract variable. So for example, this one. What we want to do is basically what this does is sets this abstract variable, or this variable, pardon me, to an abstract value like A0, and then traces that back through the code to see what the weakest precondition for that expression xh equals a0. And so we'll select that. And this goes back up through the code and computes the weakest precondition and tells you what's actually happening through the code. We can also calculate the weakest precondition directly from the code itself. We can do that same slice, and it'll turn out to be the same value. And so this is basically the precondition for having xh equal to a0. The basis of this, like I say, this was actually I've found a lot of thanks to Ryan Culpepper because I exploited his syntax browser for this. You know, Ryan and perhaps others did this part of being able to display code in the syntax browser, and also this is the original Racket, but the syntax in the syntax browser. But then we use that. We've created a multi-window version. Not a huge innovation, but it had a huge value for helping us understand the process. So this was a complicated process of figuring out weakest precondition for all the different possibilities in Racket. And so we did with the help of this. This is kind of like the developer's view of things. So where we are now is that we have a Racket prototype for all of the steps except the simplification part at the end. We envisioned connecting it to a theorem prover system. In order to do that, we didn't want to reinvent that. We haven't done that yet. But overall, okay, we kind of have a question about where to go with this. Our original business model for Autopilot was we created this body of IP, and it includes a book of 200 plus pages that details this method in fine detail, and has a body of basically lemmas to help with the simplification, lemmas that understand computer-based arithmetic and so on. And so our hope was to license that, and we did actually license it to one company who's trying to pursue this method in enterprise Java software. And so they have actually a much bigger hill to climb here, that there's all the things that seem so easy in Racket are a lot more difficult in Java. And so what we're seeing is that we believe the ideas are mature, but the implementation is now seems too challenging, and we're trying to figure out what to do next. We really want to get this capability in use, but the people on our team, one is 86, one is 82, and one is 76, and I'm the young person on the team. So we'd like it to happen in finite time. So we're thinking about sharing it with the research community. And if there's anybody who's interested in formal methods and would like to see if they could make something of this, we'd be certainly willing to help get grant funding and so on. Anyway, think about it, or if you know anybody who'd be interested in applying Racket to formal methods in one way or another, then we'd be interested in talking with them. Thank you.
Questions? Yeah, up the hand.
So the weakest precondition method relies on puns between the logical variables and program variables, which doesn't scale. How do you deal with that? 2, weakest precondition relies on formulating the every single predicate, if you want to automate it, that is mentioned in a postcondition, so it becomes more or less a functional program which extends first-order logic. So you can have a theory on top of the first-order logic. How do you deal with that? Number 3, weakest precondition does not cope with programs that have no control flow graph, which is, of course, also a question for you, but I spared you. So there are no control flow graphs for real Racket programs because you have higher order values flowing through in the control positions, and then because precondition breaks down again.
Right.
Do you cope with any of those, or you just look at very simplistic Racket programs?
Well, to answer your first question, we're going to rely on simplification to help. But yes, it's a large problem, and that's why we'd actually hoped that this special purpose hardware, this recognition hardware, would help with that simplification problem. And we haven't cracked that nut yet. We're interested. On the third problem, yeah, I don't know about I haven't looked at higher order expressions in Racket, because basically I've been looking at Racket versions of C programs and working on those. We do think we have a solution for the non-deterministic case, which we'd also be interested in applying in Racket, because Racket allows for parallel processing in multiple different ways.
Are you using Grease?
Pardon me?
Are you using Grease or Wiki for non-determinism?
We're using Dijkstra Guarded Commands.
Yeah, but then you go back to Grease and Wiki solution, which is an exponential blow up on interference between these things.
I love you guys. I guess I meant to begin this talk by saying that I appreciate having all these Racket scientists around here. I'm not a Racket scientist myself, but it is important. And then also, so we may very well be missing this kind of link between we know there's a computer problem. There's a lot of stuff we have to do in software, like going to syntax and so on. There's a lot of stuff we need to do in logic on this side, and yeah, we don't have somebody who crosses those boundaries like Amina does, and probably you do as well. And so, yeah, so yeah, that's why we're kind of asking for additional help here, and yeah, I appreciate the comments.
Great. Thank you very much.